a little bit. Yes, question?
So, sorry, going back, number 8, did you get that because the oxygen was a -2 charge or something? I wasn't sure where you got.
Let's
or
go
carbon.
through the valence electrons. Is that what you're asking about?
Yeah, I wasn't sure, because I saw that.
Well, if we look at carbon, the nonmetals, the number of valence electrons of a nonmetal is the same as their group number. So carbon is in group 4, so it has 4 valence electrons. Oxygen is in group 6, it has 6 valence electrons. There's 3 of those atoms in the molecule. So 3 times 6 is 18. And then that last 2 minus is here. So if we're counting up the total valence electrons in a single molecule of carbonate, which is a polyatomic ion, we have 24. When I first draw my initial Lewis structure, I would draw the C in the middle, oxygens in each. Then I would subtract the 6 for these 3 bonds that I made here. Following so far? Okay. That leaves me with 18. If I've got this structure and I've only got 18, I need 6, 12, 18 for those 3 oxygens plus 2 more for carbon. That means I need 20. I only have 18. So what I did over here was I double bonded. 2 bonds there. I subtracted 2 more for the double bond. Right, that's the 2 that I had to subtract for that double bond. Now I have 16. Now carbon doesn't need any more at this point because carbon is considering all of those electrons belonging to it, even though they're sharing electrons between carbon and oxygen. Carbon thinks it has 2, 4, 6, 8, so it's good with its octet. With the remaining 16, I would say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now each of the elements in the molecule has an octet. This oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. So they all have their octet. Then what we want to do when it's an ion, when you have something that's charged, that means it's an ion, you're going to put the whole shebang in these square brackets, and then you want to put the charge on the outside of the square brackets. And that's how you would depict it. Now if you're looking at resonance structures of this, remember this bond can be here, here, or here because there's 3 different bonds. So it could have that resonance structure, it could have this resonance structure, or it could have this 3rd resonance structure. Yes?
So on the exam, yours to show you all those different...
The exam question might be something like, all right, you got a molecule of carbonate. How many resonance structures would there be in this molecule? And the choices would be 1, 2, 3, 4, or 5. At this point, you'd have to draw the Lewis structure, see what bond it is that could be moving around, because that's the definition of resonance, right? It's a bond that moves in the molecule, and then figure out how many individual structures you have. Okay? All right. Yes?
Do you always include the charges? I know in the examples we didn't have the charges of the way we did on Tuesday.
If your particle that you're creating the Lewis structure for is charged, whether it's a negative or a positive charge, you always want to put it in the square brackets, and then keep the charge on the outside.
Okay.
Because that tells the reader that this is something that has an extra charge, and so if they're trying to look back and see, what is this thing, they know it's a charged particle.
Okay.
Because it has a different kind of
Okay, so as long as it has that.
has a square brackets with a charge on it.
Okay, thank you.
I think I missed the previous class, not before last class, but the one before that, on Monday, no, last Wednesday. For the carbon, where is it, why is it needing 8?
The octet rule, all
Okay, so
bonding
it's a part of
occurs.
that.
All bonding occurs to satisfy the octet rule. In ionic bonding, that's between metal and non-metal, the metal gives up an electron because it usually has only 1 or 2 valence electrons, right? And so it gives up those 1 or 2 valence electrons. It reveals an inner shell that's full. So that's the driving force in ionic bonding, is something's given up electrons, the non-metal's taken them. Non-metals usually have 6 or 7 or 8 valence electrons. They get a couple more. Now they have a full octet. So that's the octet rule in ionic bonding. Octet rule in covalent bonding is different. The octet occurs when elements share electrons, and each element considers the pair or multiple pairs that's shared in between them
Okay, so-
as belonging to them.
So like for this one.
Right, and what happens is, and the reason that that's true is, say for example, this pair of electrons, they spend some time around this oxygen, they spend some time around this oxygen, so it sort of fools the oxygens into thinking that they've got their full octet. And what they want is that full octet gives them the most stable electron configuration, the most electrically stable. So it's going to be at the lowest energy state, which is what everything in nature wants to be. You don't want to be at a high energy state and expending a lot of energy, right? When you can be at a lower energy state, and that's why this octet rule works.
Okay.
Because that's the lowest, most stable energy state of all components.
I did miss that class.
All right, sure. Now that's actually a good question. So resonance. We've talked about resonance, different types and molecules. There's our. So that's a different one. Also has resonance. Oh, when you get to organic chemistry, does anybody know what these things are called? Ever heard of this stuff in organic chemistry? The rings. It's a hydrocarbon ring. Say that again. Benzene ring. Very good. When did you have organic chemistry? Ah, very cool. So yes, that's a benzene ring. And in organic chemistry, which most of you have not had before, they could talk about hydrocarbon chains and hydrocarbon rings. A benzene ring is carbon at each one of these little corners, and then it has little hydrogen sticking out. And when you get to, how many people got to take organic chemistry in here? All right, when you get to organic chemistry, you talk all about benzene rings, and then you talk about functional groups that stick off of these benzene rings. Well, in chemistry, we abbreviate a benzene ring. We don't want to put all that stuff in there. We just put the double bonds and the single bonds. So there's carbons at each one of these corners, and there's double bonds and single bonds and double bonds and single bonds, etc. All right, here's a chemistry joke for you. All right, if this is a benzene ring, right, what's this? Mercedes benzene. Ah, there you go. My son has a Mercedes. He's a 24-year-old that wants to be a politician. I told him that joke, and he just rolled his eyes. So he doesn't get it. He doesn't get it. Probably because he's not a scientist, right? You know, that's actually important for your intellectual development. If you have humor in the context of something you're learning, not only does it help you understand that thing better, but it also helps you feel like you're a member of that club, right? You're a member of the chemist club because you got some chemistry jokes. So next time you go to a cocktail party, yeah, right, and you're talking to a chemist, you can say, hey, I have a chemistry joke. You want a physics joke? My physicist's son, I showed him this physics joke. He thought it was hilarious. All right. Anybody in physics? What's that symbol in physics?
Oh my God.
Chemistry got some funky symbols, but physics got even more funky symbols. What's this in physics? I heard it's a resistance, but better off, it's the ohm. Okay, that's an ohm. It's an ohm, it's a unit in physics. All right, that's an ohm. What's this? A mobile ohm. So now you have a whole repertoire of jokes for both chemistry and physics. And the next time you want to engender respect amongst chemists or physicists, you can tell them that joke, and now you have insider information, right? All right. So there's a few exceptions to the octet rule. Sometimes there's a few odd electrons. You throw those on the central atom. Sometimes there's too many electrons. You throw those on the central atom. All right. So there's a molecule that violates the octet rule. How many electrons does phosphorus have around it? 10. Okay, it is possible, but you've got to put this stuff under high temperature or high pressure in order for that particular thing to occur. You know what? Let's do that structure. It's PCl5 so that you can see how it would work out in Lewis structures. So do it next to the mobile ohm and the Mercedes benzene ring. All right, phosphorus has 5 valence electrons. Chlorine has 7. Each times 5 is 35. So we got a whopping 40 electrons to distribute. Phosphorus in the middle. 1, 2, 3, 4, 5. That doesn't look right, but we'll just go for it. Minus 10 gives me 30. If we put a chlorine on each of those peripheral spots, how many valence electrons does each of those chlorine need? 6. So 6, 12, 18, 24, 30. That's how it works in Lewis structure terms. So there's your, you put 6 dots. I just put 1 dot, but 6 dots around each of those chlorines. All right, so covalent bond strength. Now we get into covalent bonds are when electrons are shared. Remember we talked about lattice energy. Lattice energy is in relation to what kind of compound? Ionic. So when we discuss lattice energy, you're talking about crystal structure of ionic compounds. Now we're talking about bond strength. We're talking about covalent compounds. We're talking individual molecules and individual molecules as they take place in chemical reactions. Average bond enthalpies there's a table of average bond enthalpies in the back of your textbook. We're going to use these average bond enthalpies in just a minute to figure out a chemical reaction here. All right, so this is another energy diagram that Brown and May, the authors of your text, have shown you. And what this diagram is showing is the breaking of bonds, how it costs energy, and then when bonds are formed, energy comes back into the system. So if we started out here with CH4 and Cl2, so CH4 and Cl2, we'd have to break the bonds here, we'd have to break some bonds here. That means you have to put energy in. So as you're adding energy, is that going to be an endothermic or an exothermic reaction if you have to add energy in? Endothermic, so you have to add energy in. So the reactants are at a lower energy state than the products are in this case, and that's because we're going to be adding energy into the system, endothermic. Once you get up to this point, then you're going to be making new bonds. Making those new bonds capture some of that energy, and in fact you get more energy back in the bonds that you created than the original expenditure of energy that it cost you to break the original bonds. So if you look overall here, it starts, these ones start here, these are at a lower energy level, so it costs you energy here, you got energy back, but overall in the end, this was an energy producing reaction because even though it cost you some, you got more back than what you had to use. So if we look at that as, I'm going to write this reaction on my paper. I'm going to ask you to do the same because then I'm going to have to switch over to the ladybug. So you're going to write down CH4 as a gas. I'm going to do it in landscape so it's easier to see. So CH4 as a gas plus Cl2 as a gas, which yields CH3Cl gas plus HCl as a gas. All right. So what you have to do in these kind of examples is you've got to draw Lewis structures to figure out what it is that the bond enthalpies are doing when they are, get these a little closer here. All right, now you guys can see the bond enthalpies there in relation. Now I'm going to go back to the ladybug, and we're going to draw Lewis structures for each of the individual molecules in the chemical reaction. Uh-oh, doggone it. Always happens when I do this. There we go. All right, what you want to do is CH4. So CH4, I'll do it in pencil, has 4 valence electrons for carbon. Hydrogen has 1 each, there's 4, that's a total of 8. If we draw the Lewis structure for CH4, it would be carbon in the middle, 1, 2, 3, 4 bonds. All right, so there's the Lewis structure for CH4. Let's count electrons for Cl2. Chlorine is a halogen, there's 7 valence electrons times 2 is 14. So we have 14 valence electrons to distribute. So I'll do Cl2 here. So 14 minus the 2 for a bond leaves me 12. That makes good sense. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Bless you. CH3Cl. Each carbon has 4. 3 more for those 3 hydrogen, and chlorine has 7. So we're looking at a total of 14 for CH3Cl. This is an organic compound. They give you an idea of how it is put together by the way that they write the order of the elements. So you've got a C, and remember, hydrogens can only be peripheral atoms because they only have one ability or one spot to bond. So that's what this molecule is going to look like. Right? Got CH3Cl. So now I've used 2, 4, 6, 8 for those bonds. I've got a total of 6 left over. Right? So now where am I going to do those last 6? Do any of these hydrogens need more electrons? How about carbon?
Yeah.
Oh,
Or
sorry.
chloride and chlorine.
I think carbon's pretty good. Carbon thinks it's got 4. Chlorine needs how many? Well, that's handy. 1, 2, 3, 4, 5, 6. And finally, good old HCl. Hydrogen has 1, chlorine has 7. There's a total of 8. I'm going to draw HCl. It looks like this. Subtract the 2. Leaves me 6. What am I going to do with those last 6 electrons? Alright. So now we know what these doggone molecules look like. So those two are added together. They make these two. Now what the book is going to tell you is that you selectively break the bonds and then you make the ones that you selectively broke. I'm going to show you something different that will decrease the attempts or the opportunities for error. If you look back at the PowerPoint, the formula that we need to solve this is, where's my formula? There it is, the bottom of the page there. Delta H of the reaction is the sum of the bond enthalpies broken minus the sum of the bond enthalpies formed. And that's because this is going to cost you energy, right? Breaking bonds is going to cost you energy. Making bonds, you get the energy back. So what you want to do is you're going to take the sum of all the things it cost you to break it up, and then you're going to figure out all the ones that you get when you bring them back again. So we're going to take that idea now over to the Ladybug. Say delta H of the reaction is equal to the sum of the bonds broken minus the sum of the bonds made. Alright, so now what I want you to do is you're going to look on your table of bond enthalpies. The first one we need to do is look for CH bond enthalpy. So if we go back to our slide, there we go, CH bond enthalpy. Do you see this? Is that it? No, we need another table. There's a better table here. Here we go. This is the one we need. All right. There we go. CH bond enthalpy is 413. So you would, how many of those bonds do we have to break?
4.
So we're going to say, in parentheses, 4 times, what's the number that we need there?
Is it 4?
Right, because if you look at the molecule, CH3, get out of this to go back to the ladybug, right? Go back to the ladybug,
Okay.
right? See, we've got 4 bonds to break. 1, 2, 3, 4.
Okay.
So I would take 4 times the 413, right? Plus, now I got to break the chlorine-chlorine bonds. So we go back to our table of bond enthalpies. And I know this is in your appendix. I believe it is also in the slide, so you can look. All right, what's the next bond? The CL-CL bond? How much is that going to cost us? Where's CL-CL? 242. And how many of those have we got to break? Just one. So 242, close parentheses, minus, now we got to sum everything that the bonds that are created. So now if we go back and look at the bonds that are created, what kind of bonds do I have to make here? We got to make 3 of those CHs, so 3. And what was the CH bond? I think it was 413, right? 413 plus, I got to make a carbon-chlorine bond. So now we got to look back at our table of bond enthalpies. And the carbon-chlorine bond, do you guys see it there?
328.
328. All right, so add 328. Plus, we still have one more bond. This hydrogen-chlorine bond that we have to make. So the H and Cl bond, where's that? 431. All right. Plus 431. All right, so now you do the math of that. And it should come out to, let me show you what the authors of your textbook prefer for you to do. All right. What the authors of your textbook is, they're summarizing it here in the words after, in this example. 1 CH bond and 1 CL-CL bond are broken. If we look back at the ladybug, that's true, right? So in order for this thing to make this thing, right, you had to break one of those bonds, and what else? You had to break this bond. So you really only needed to use those 2, but then you make that one and you make that one. And so the authors of your text say you could do it that way. You can isolate only the bonds broken and only the bonds made. But to me, I think it's easier if you do all the bonds breaking them up and then all the bonds making them, because then you never know if you're picking the right things that are broken or being made. So you choose however you want to do. Okay? All right, so let's do the quiz. Take out a sheet of paper.